Tropical regions are among the hottest and most humid places on Earth, but also the coldest and driest. Yep, you heard right. While temperatures on the surface can range from 80 to 90 degrees Fahrenheit all year round, they can dramatically drop as you go up in altitude. In fact, as you get closer to the stratosphere, they can be as low as minus 110 degrees Fahrenheit. This extremely cold region between the troposphere and the stratosphere is called the tropical tropopause layer.
In the tropics, it's very warm and moist down here at the surface. When you get up to the tropopause layer, it's very cold and dry.
So it turns out that the tropopause is actually coldest in the western Pacific.
Right above Guam is an ideal place because it is the coldest and the driest part of the tropics.
Everything is ready for the second phase of the field experiment. We are 13 degrees north of the equator in the Pacific, our new home away from home for the next several weeks. We are in Guam.
So the tropics are the part of the planet that gets the warmest from the heating from the sun because it gets the most sunlight on average.
Because the surface is so warm and there's so much water, you evaporate water, liquid water becomes a vapor, so you have this very hot, moist air down here at the surface. So this is air that's got a lot of energy. And just like a boiling pot of water, it can rise very high.
And it tends to pull other gases that come from the surface up with it. So this is the part of the world where most of the circulation getting up from the surface up into the upper part of the troposphere and into the stratosphere, this is where it occurs.
So here in the tropics, we see these thunderstorms boiling up to very, very high altitudes. And so we have a very high elevated tropopause here in the tropics.
As you get convective processes going, the air rises. As you know, if you take air and you expand it, it cools really fast.
And it turns out that, in fact, the warmest places in the world are in the tropics, but about 55,000 feet above us, about 16 kilometers, is one of the coldest places on Earth.
So what that does is, as it cools really fast, all that water vapor in the air going up gets squeezed out. It's like wringing a towel, and all the water starts to squeeze out. So you get cloud processes formed, it squeezes out the water. The air that comes out the top tends to be dry.
You still get some water making it up to the tropical tropopause, and there the atmospheric motions transport air into the stratosphere. So air is transported into the stratosphere with a small amount of water that's left behind.
And this is the area that tends to be the controlling mechanism for how much water gets into the upper troposphere and then onto the stratosphere.
So if you want to understand the composition of the stratosphere, how much water there is, and how much ozone-destroying substances or trace gases there are, you need to go to the tropics and study the region around the troposphere and the tropics.
So this is the spot to be. So this is the area where the ocean gets the warmest, the convection is the strongest, and then the air that comes out the top gets the coldest.
And we've known that for many decades, and for at least 20 years we've known we really need to go to the Western Pacific to study the extreme dehydration where the tropopause is coldest, and where the most extreme dehydration to low water vapor concentrations occurs.
Now, Guam is the coldest and driest part of the tropics.
It's actually a warm region at the surface and a cold region at the tropopause, and Guam is right in the center of action. Plus it has the airfields and facilities we need to operate our high altitude aircraft.
It takes a lot of work to plan a remote deployment of this size.
Yeah, preparing for a mission where we're deployed, where we have to take the entire team and the aircraft and all of our equipment, is really quite an effort.
Making sure we had a hangar available to us, making sure we had office space available, making sure that we had areas that we could set up our aircraft control trailer and our instrument control trailer.
It's also difficult because you're away from where you built your instruments, where you operate your aircraft. So if you have a problem, you have to ship everything here.
Because when you're this far from home, so to speak, you know, you got to have everything here, not just the airplane and the people, but all your equipment, including spares.
Actually, all the work that's gone into this ATTREX project has been one of the most difficult things I've ever done.
So when we operate out of Edwards Air Force Base, we operate from a fixed structure called the Global Hawk Operations Center. That's the main command and control center for the NASA Global Hawks.
Well, what's different from operating here in Guam versus operating back at Edwards is we have these mobile ground stations. So that's where we fly the airplane and operate our payloads from.
So the front room, the flight operations room, is replicated with a 40-foot trailer with all the communications equipment, all the computers, all the servers, everything. And then we have another trailer that replicates the 14 workstations that the payload operations room has, and that's in another trailer.
And we're basically providing the same functionality from Andersen Air Force Base in a forward location that we would have back at Edwards Air Force Base.
We can deploy anywhere in the world with these trailers as long as we have the appropriate setup.
Okay, that sounds like a good plan. So we're ready for airplane.
For the ATTREX campaign, the NASA Global Hawk is basing out of Andersen Air Force Base. And from Andersen Air Force Base, we'll be flying north all the way up to the Aleutians, east towards the Philippines, south down by Australia and New Zealand, and out to the east all the way to about Tahiti, the other side of Hawaii, basically. It's roughly about a 4,000 mile radius of range that the Global Hawk has from here at Andersen Air Force Base.
We really have daily meetings. I know certainly the forecasters, the modeling group, and our pilots meet almost every day whenever we're getting ready for a flight. We are working every day on the aircraft, working with the scientists. They've got to pre-flight their instruments. After flight, they've got to post-flight their instruments. Some want to come off, some don't want to come off. So it's a constant ballet of activity around the airplane in between flights until the day when we're ready to go. Everyone comes on. We'll have engine start at 5 o'clock, which means they've got to come in at 11 o'clock at night, work till 2 a.m., do their thing with the instruments. Then our crew comes in, buttons up the jet. It's rolling out at 4 o'clock. Engine start at 5, take off at 6. So it's an ensemble of people all doing really great work together to make this whole thing happen.
And at 872, we have a good power transition, good engine start.
And Trapper, can I get a takeoff report?
Yes, sir. Runway's clear. You're going for takeoff.
Roger that.
Three, two, one.
So the Global Hawk has great capability with tremendous range and endurance.
So many lessons learned from this campaign that will make our Global Hawk operation a much more globally deployable package.
And as we've demonstrated, we can do a lot of science from Dryden, California, or we can deploy, as we've illustrated here, to reach out. And I think we've shown now that we can really go almost anywhere in the world.
Because this is our first deployment away, really away from the mainland. This will be our first, it won't be our last, and we will be well suited to take our show on the road anywhere in the world from now on.
We're collecting data over the tropical Western Pacific, data that will improve our understanding of our atmosphere, weather, and climate. The ATTREX mission will help us better comprehend the world we live in, to learn more about this planet we call home.